Okay, so in the first part of this video, I'm just going to talk about how to prepare or how to sketch a curve in order to answer questions. And so I'm going to be starting at slide 19, working on example 3. So in slide 19, we're told that whenever we're trying to find probabilities using the normal distribution, the first step is to always sketch a curve, label it, and shade the area of interest. This is going to help us when we're actually trying to solve probabilities, and is another way for us to make sure that our answer makes sense. So moving on to example 3. So here we're told let n 18,3, so normal distribution, with a mean of 18 and a standard deviation of 3, represent the age distribution in this group. So that notation was covered earlier, but I'm going to go ahead and just write it down right here again so that you know what it means. So the n stands for normal distribution, so I'm just going to call that normal. The first number is always going to indicate the mean. So normal, mean, and then the second number will indicate the standard deviation. So mean and standard deviation. So whenever you see that notation, always remember our data is normally distributed with the mean of whatever that number is and a standard deviation of whatever that number is. This information will be very important for us when we actually begin sketching or solving problems. So the first thing that this example wants us to do is to draw a picture that represents our model. So our model is normal with a mean of 18 and a standard deviation of 3. So we know that if we have a normal distribution, then it must be unimodal and symmetric. The peak is going to be the mean. This is something that we learned from chapter 3 already. So the mean in this case we know is 18. And the standard deviation is 3. And so we know that one standard deviation above the mean will be 21. 2 above will be 24. 3 above is 27. And then we also know what these 3 values are too. So here I've drawn my curve, I labeled it, and now moving on to the second part of this example, I want to shade the probability of selecting a student who is older than 20 years old. So based on the model that I already drew right here, I want to shade the area that corresponds to a student who is older than 20. So I'm going to look at where 20 is on my line. So 20 is going to be right around here. And we're looking for the probability of selecting a student who is older than 20. So we're going to shade to the right. And so the area that corresponds to that is what I've shaded right here. Now the next part wants us to shade the area that corresponds to selecting a student between 17 and 19 years old. So 17 is going to be right here. So I'm just following the same steps before. 19 is going to be right about here. And so the area or the probability of selecting a student who is between 17 and 19 is what I've shaded in red. Finally, we want to shade the area that corresponds to selecting a student who is younger than 17. So here I've marked 17 already, but we're looking for the area or the probability of selecting a student who is younger than 17. So we're going to be shading to the left this time. So everything that I've shaded in blue right here will correspond to the probability of selecting a student who is younger than 17. So sketching the curve, labeling it with the proper values, and shading it is the first step for us to do in order to find probabilities. Okay, so moving on, we're going to talk about the standard normal model. So I want to make a clear distinction between what is a standard normal model and what is just a regular normal model. So a normal model is like what I have right here, what I have drawn. The normal model is unimodal and symmetric, except that these values right here are going to depend on our data. So here my data is based on the class. So these values are data values. Now for a standard normal model, the assumption or the requirement is that the mean, mu, is equal to 0, and the standard deviation, which this symbol right here is known as sigma, so the standard deviation is 1. Those are the main assumptions behind the standard normal model. So why is the standard normal model useful? Number one, it helps us find probabilities for any normal model. So whenever we have just a normal model like the one I've drawn right here, I can't find the area under the curve because each data set will be unique, so it's not guaranteed that using this picture that I drew right here, I can find the area for a completely different problem. Number two, the standard normal model is useful because we can transform any normal model into standard units. So I can go from a model like what I've drawn right here into a standard normal model, and then using that standard normal model to find probabilities. And then number three, if we can transform a normal model into a standard normal model, then we can easily look up the areas and probabilities using a published table. And that table will be available in these two appendix sections of your e-text. So to kind of illustrate what I mean, so again here, you begin with a normal model. This is going to be specific to your data. You have your mean value, you have x values, you have your own standard deviation. And then you want to transform it into a standard normal model where the mean now is assumed to be 0. The values are going to be standard units instead of data values. And then your standard deviation is assumed to be 1. And in order to make that transformation, we use the z-score transformation. So this z-score formula right here is basically the same thing as we did in chapter 3, except now instead of using x bar, we use mu. Instead of using little s, we use the sigma symbol. So again, in order to go from a normal model into a standard normal model, we need to implement a z-score transformation. Okay, so after you make that transformation, you're going to get a z-score. And what you would do with that z-score is you're going to use a table like I have here. Again, that's available in Appendix 2 and 3 of your e-textbook. But basically, you're going to use that z-score in order to find an area. And so let me explain very quickly how this table works. So here, you see there's a z for the first row and the first column. That's going to represent your z-score. Anything else inside of the first row and column will be the area. And so the way that you would look at the z-score is the column only gives you the number before and after the decimal, but z-scores are usually given to the 100th decimal place. And so that's where the first row comes into play. The row is going to correspond to the 100th decimal number. So again, the column only gives you the number before and after the decimal, but then the row is going to give you the 100th decimal number. Okay, so to illustrate how this works, or to get you familiar with using this table, let's look at these two quick examples right here. So the first example, we want to find the area that corresponds to a z-score of negative 2.31. So here again, the number that I'm given, or the number before and after the decimal, is negative 2.3. So in this first column right here, I'm going to be looking for negative 2.3, which is right here. Now, my 100th decimal number is 1. So I'm going to match negative 2.3 to a 1, or to a number, or to the row that has 1 in the 100th decimal place. So if I match it up, then here I see that this number right here, 0.0104, is what corresponds to a z-score of negative 2.31. So the z-score uses the first column and row in order to find the area. The area is going to be where these two numbers intersect on the table. So for this example right here, when the z-score is equal to negative 2.31, area is going to be equal to 0.0104. Okay, now the next example, same thing, except we're looking for the area that corresponds to a different z-score. So if we had a z-score of negative 2.97, what would be my area? So here, the number before and after the decimal is negative 2.9. So here in the first row, or in the first column, I'm going to be looking for negative 2.9, which is going to be right here. My 100th decimal number is 7. So in the first row, I'm going to be looking for 0.07, and I'm going to be matching them up. So here, I have negative 2.9 and then 0.07. So they intersect at this number, 0.0015. So when my z-score is equal to negative 2.97, my area is going to be equal to 0.0015. Okay, so now that I've talked about how to find area using a table like this, based off of the z-score that you obtain, I want to go over a quick summary of how to find normal probabilities. So to find normal probabilities, it's basically reduced down to these 4 steps. So again, step 1, you want to draw the curve, label it, and shade the area of interest. Again, this is very important for you because when we start finding normal probabilities, there are a few different types of examples, and so by shading the area of interest, it'll help you make sure that you're on the right track. Step 2, performing the z-score transformation. So again, we want to go from a normal model to a standard normal model so that we can use a table like this to find area. Step 3, once we have the z-score from step 2, we want to find the area that corresponds to that z-score using the normal distribution table. And finally, step 4, making a conclusion. So step 4 isn't as simple as it looks right here, because depending on the example, whether we're shading to the right or we're shading to the left or we're shading between two numbers, this conclusion part or the step 4 might be a little bit more complicated than just saying, oh, here's the area. And so in the next video, I'll go through examples, 3 main types of examples that you'll see, and how to properly complete all of these steps.